let me discuss about the construction of root locus. As I was mentioning in the previous class that you don't have to follow the lengthy methods such as the inspection method wherein you physically find the roots against each variation in k factor, right? So what you can do is you can go for the Evans method or the root locus method. Now, the root locus method is based on several rules. So using these rules, you will be able to construct uh, the movement of closed loop poles when a certain parameter is varied. Okay, so let us look at the various steps which are involved in constructing a root locus. Okay. So rule 1 is about symmetry. So root locus, in short, let me write RL. Root locus is always symmetrical about real axis. Okay, and I have given an example also. Now, what do you mean by symmetry? Say, for example, you have a two-dimensional plane. Okay, let's say you have got the graph as something like this. Now, symmetry in the sense the mirror image should appear in the lower half of the graph as well. So mirror image will be something like this. So this is called as symmetry. So when you do the paper fold along the real axis, so basically this image will merge with the bottom image. So that is called symmetry. So always your root locus going to be symmetrical about the real axis. So that's your rule number 1. Rule 2. Okay. Rule 2 is about the information of open loop poles and open loop zeros. Okay. So let us define. P is equal to open loop pole count and Z is equal to open loop zero count. Okay. So what you have to do is from the given open loop transfer function, you have to count how many open loop poles are there and how many open loop zeros are there. You can include real poles as well as complex conjugate poles. Similarly, real zeros and complex conjugate zeros can be included while calculating P and Z. Okay. Now, once we get P count and Z count, you have to compare P. Okay. Compare P with Z. Okay. Now, when you compare P with Z, you can get three possibilities, right? You may have P count greater than Z count, or P count less than Z count, or P count is equal to Z count. Okay. Now, on the basis of these three cases, you can predict about the root locus existence. All right. So let us consider these three cases independently. Okay. So imagine that. Okay. So let's consider case 1. Imagine that you have P count greater than Z count. That means to say number of open loop poles are greater than number of open loop zeros. Okay, if that is the case, the root locus branches. The root locus branches. Okay, what you can say, number of root locus branches, n is taken as the pole count. Okay, pole count. For example, let us say you have poles as 4 and zeros as 3. So for example, you have got 4 poles in your open loop transfer function and 3 zeros in your open loop transfer function. So when you compare P with Z, obviously you would find that poles are greater than zeros. So if that is the case, the number of root locus branches are nothing but the number of poles. Okay, and how much is it? 4 branches. 4 branches. So this is what I was predicting. So in this particular open loop transfer function or system, you have 4 root locus branches. Okay. Now out of 4 branches, and one more thing I wanted to tell you, the open loop poles are called as starting points. Open loop poles are also called as starting points, and open loop zeros are called as terminating points. Terminating point. Okay. Starting points are those points at which a root locus branch emerges, and the terminating points are those points at which the root locus branch is going to get terminated or is going to get end its journey. All right. So out of 4 branches, Z number of branches terminates at the available zero. Out of 4 branches, Z number of branches terminates at the available zero. What do you mean by that? How many branches did you have? 4 branches. And how many zeros did you have? 3 zeros. So Z number of branches. So the understanding of the statement is that Z number of branches. So what is the Z count? Is 3. So 3 branches. So out of, I should be taking out of P branches. The general case I should consider, and I should explain the general case for a given pole and zero count. So out of 4 branches, um, 3 branches are going to terminate at the available zero. Terminate the zeros. Okay. And remaining P minus Z branches move towards infinity. Alright. So we started with 4 number of branches. Out of 4 branches, 3 are getting terminated at the available 0. And the left out count is 1. So one particular branch will move towards infinity. So in our case, 4 minus 3 is equal to 1. So one branch move towards infinity. Okay. So this is the median. Okay. So that is for case number 1, wherein pole count is greater than the 0 count. Alright. So let me erase and let me move towards case 2. Okay. You may have transfer functions in which 0 count is greater than pole count. 0 count is greater than pole count. Okay. If that is the case, then the number of branches, number of root locus branches are n is equal to z, Whichever is greater, those many branches of the root locus exist. So in our case, we have assumed z is greater than p, so number of branches n is equal to z. All right. Now, out of z branches, okay, so out of z number of branches, okay, p branches terminate at the zeros. Okay, that is because poles are the starting points and zeros are the terminating points. So starting point should terminate. Okay, should end up at the terminating points. Okay, so some reasons these terminating points are also called as sinks. Okay, so out of z number of root locus branches, okay, p number of branches are terminating at zeros. Okay, what do you mean by that? Let's say suppose you have open loop pole count as 3 and open loop zero count as 4. Okay, so obviously 4 is greater than 3. So when z count is greater than p count, you would say that the number of root locus branches are z, that is 4. Okay, so this particular system will have 4 root locus branches. Out of 4 root locus branches, p branches, and what is the p count? 3. 3 branches terminate at zeros, and the remaining p minus z branches, z minus p, because z count is greater, right? Remaining z minus p branches originate from infinity. Remaining z minus p branches originate from infinity and move towards the available zero. Okay, so this is the meaning. So remaining z minus 3 branches. So how much is it? 4 minus 3 is 1. So one branch will originate from infinity and move towards the available zero. Okay, that's because you always have one surplus zero, because zeros you have had 4 and poles you have had 3. So you have one leftover zero. So what happens is that one branch will start from infinity and move towards the available zero. So this is the second possibility. All right. Now the third possibility is that you may have pole count is equal to zero count. The third possibility. So case 3. P is equal to z. Say for example, you have 3 number of poles and 3 number of zeros. P is equal to z. If P is equal to z, then the number of root locus branches is equal to basically n is equal to p is equal to z. The same count, doesn't matter. Okay. Now, since you have equal number of poles and zeros, so all the branches start from poles and terminates at the available zero. Okay, that's because let's say poles, you have 3 poles, say P1, P2, P3 poles, and you have 3 zeros, let's say Z1, Z2, Z. So since you have equal count, So what happens is that pole P1 may terminate at Z1, P2 will terminate at Z2, and P3 terminates at Z3. So there is no extra branch which is left out, as in the previous case you have seen. You may have P minus Z left out branches or Z minus P as the left out branches. So in this particular case, you don't have any surplus branches. So for every starting point, you get an terminating point. Okay. So such problems basically gives circular root locus plots. Okay. It's an interesting property. Whenever p is equal to z, such problems basically give circular root locus plots. Okay. So these are the three possibilities. Rule 3. Okay. Rule 3 is about identification of root locus sections. So subheading of rule 3 is identification root locus sections on real axis. Okay. Now, to identify root locus section on real axis, probably you can use the following steps. Okay. First step is to plot the pole 0 plot. Plot the pole 0 plot from g of s into h of s info. All right. Let's say, for example, we get the following plot. Let's say I have a 0 here, pole at origin, and let's say 0 here, and one more pole here. This is positive sigma, and this is your negative sigma. Okay. Remember one thing, rule number 3 is applicable only on real axis, that is plus to minus sigma axis. So rule number 3 is not applicable in the complex zone. All right. So it is applicable only in the only on the real axis. Okay. So mark the sections on each of the poles and zeros on the right hand side. So you have a 0 here. So I have marked a section just on the right hand side of this particular 0. Similarly, section 2 is also found on the right hand side of this particular 0. So as section 3 and so as section 4. And compulsorily, you will have to select a section at minus infinity. Alright. Once that is done, you can start with the first root. For example, over here, we have our first root as a 0. So cover this 0 and count how many poles and zeros are lying on right hand side of this particular section. So you don't find any poles and zeros, right? So the count is 0 and 0 is considered angle of centroid. Okay, centroid. Okay. Now, definition of centroid is pretty simple. Centroid is the meeting point of asymptotes. Okay, centroid is nothing but meeting point of asymptotes. Asymptotes. And morning I have mentioned that asymptotes are nothing but in root locus. Okay, not in mathematics, in root locus. Asymptotes are the guidelines for the branches of the root locus moving towards infinity. So they basically serves as the guidelines for the branches of the root locus which are moving towards infinity. All right. So centroid can be calculated with the following formula. Centroid is denoted by sigma, and sigma is equal to summation of real part of all the poles minus real part of zeros divided by p minus z. P minus z. Okay. Okay. Poles of what? Okay. Real part of poles of open loop transfer function. Okay. I can just write g of s into h of s. So the second part is minus summation of real part of all the zeros of g of s into h of s divided by p minus z. I have already mentioned, right, what is p. P is number of open loop poles and z is number of open loop zeros. So it is pretty straightforward. Okay, now you can substitute all the real parts and you can find out the centroid. Pretty simple. Okay. Next, rule 5. Okay. Rule 5 is angle of asymptotes. So you know what are asymptotes, right? The guidelines for the branches of root locus which are moving towards infinity. Now, with what angle you are supposed to draw those guidelines? So the angle of asymptotes is basically given using the following formula. So angle of asymptotes is denoted by theta, and theta is given as this formula 2q plus 1 into 180 degree. The angle condition, basically you are using angle condition. Okay, morning we were discussing about it, right? 2q plus 1 into 180 degree divided by p minus z, where q is equal to 0, 1, 2, so on and so forth until p minus z minus 1, where p is open loop pole count, z is open loop zero count. Okay, so that's how you can find out theta. Say for example, if you get, say, q is equal to 3. Okay, that's the reason I have written, say q is equal to 3. So q is equal to 3 means 0, 1, 2. Okay. Or better way of writing is, that's a little confusing. Let us say 0, 1, 2. The count is 3, which is consisting of 0, 1 and 2. So what you have to do is you have to find theta for each q naught value. So for q is equal to 0, let's say the angle is theta 1. Okay. And for q is equal to 1, let's say angle is theta 2. Similarly, for q is equal to 3, your angle becomes theta 3. Okay, what is theta 1, theta 2, theta 3? You will be able to calculate provided you know the pole count and zero count. That doesn't matter. When we solve numericals, you will be able to understand. Okay, but you have to understand the fact that this factor q, okay, which in turn depends on this factor, that is pole count and zero count, right? So due to the presence of poles and zeros, the angles are going to change. All right. So that is your rule number 5. Very easy. Directly you can substitute and you can get the value. Okay. Rule number 5. Next up, you have rule number 6. This rule number 6 is also called as breakaway points. You can write calculation of breakaway points. Breakaway points. Okay. So sometimes in some problems, instead of breakaway phenomenon, you may encounter breaking phenomenon. But analytically, they are the same. Breakaway or breaking. They can be found using the following method. Now, how to calculate breakaway points analytically? So to calculate breakaway point, okay, the following steps can be used. First, you write down the characteristic equation, that is f of s is equal to 1 plus g of s into h of s, okay, is equal to 0. All right. once you write down the characteristic equation, in the second step, rearrange the equation in such a way that you get k is equal to f of s. That means to say for example, okay, I'm just giving an example. Let us say you have the characteristic equation as a square plus 2s plus 1 plus k is equal to 0. What you can do is you can write k is equal to minus s square minus 2s minus 1. Okay, or k is equal to minus of s square plus 2s plus 1. Okay, so rearrange the equation. Something like k you have on left hand side and factors of s you have it on right hand side. Okay, so this manner. Okay, I have given the example straight away. Okay, once you are done with the rearrangement, what you can do is differentiate k with respect to s and equate it to 0. Differentiate k with respect to s and equate it to 0. Okay. So by doing so, what do you get? You get dk by ds and you equate it to 0. So basically when you equate it to 0, you get roots of the equation. Roots of the equations. So these roots are nothing but the breakaway points. So these roots are nothing but the breakaway points. Okay, so this is how we calculate or find the breakaway point. Okay, let me quickly wrap up. Write down the characteristic equation, rearrange the characteristic equation in such a way that you keep k terms on one side and s terms on the other. And then you perform dk by ds and equate it to 0. When you do that, you get the roots of the equation. And the roots of the equations are nothing but the breakaway point. Okay. Since we have taken an example for k, you can quickly do the step number 3. Okay. So dk by ds. Okay, let's do that. So dk by ds. Okay, I'm writing example is equal to, okay, minus term, let us keep it 2s plus 2 is equal to 0. Okay, so we are equating it to 0, right? So this negative sign gets absorbed. So you get 2s plus 2 is equal to 0, or s is equal to negative 1. So negative 1 is the breakaway point. Okay, breakaway point. So it is something like, if you have a second order equation, when you differentiate, what do you get? You get a first order equation. When you get a first order equation, when you equate that first order equation to 0, how many roots you are going to get? One single root. So basically, if your characteristic equation has 4 roots, the breakaway equation will have 3 roots, because when you differentiate, the order of the equation gets reduced by 1. Okay. So against 4 roots, you will have 3 roots. In our example, we have taken a second order system, due to which you are getting only one single root. So this is called as the breakaway point. Okay. Now this breakaway point is connected to rule number 3. Okay. What was rule number 3? Rule number 3 is identification of root locus sections. Okay. Let's say, for example, you have got some 3 breakaway points. Say we have got 3 breakaway points. Okay, breakaway points, in short, BA. Okay, 3 breakaway points. Let's say S1, S2, S3. Okay, and you want to know whether all the 3 breakaway points are valid breakaway points or not. So to check whether they are valid breakaway points or not, what you have to do is you have to place these breakaway points in rule number 3. Rule number 3 is about existence of root locus branch on real axis, right? So let's say our rule number 3 prediction was something like this. Okay, say I have a 0 here and I have a pole here. Right? This is your RL because OR, NRL, okay, and this is RL and this is NRL. Okay, I've just considered. Huh? Okay, I've just considered. Okay, let's say this is at plus 1, this is at origin, minus 1 and minus 2. Okay, and let us say our breakaway points are, let's say, 0.5, comma, minus 0.5, comma, minus 1.5. Okay, let us say when we differentiate and when we equate it to 0, we get the following breakaway points. Okay. Now, how will you check the validity? You can simply place these breakaway points in your pole 0 plot. Okay, for example, I have taken a sample pole 0 plot here in which I have marked alternate sections of, okay, so this is actually RL, I'm so sorry, this is NRL, okay, this is RL, NRL, and this is R. So point number 1, what is the value? 0.5. So where is 0.5? 0.5 is here, right, between 0 and 0.1. So this 0.5 is getting placed in which section? NRL section. Hence, it can be called as invalid. Invalid. So you can discard this point. Fine. Next we come to minus 0.5. So this minus 0.5, where is it getting placed? It is getting placed somewhere over here. So between 0 and 1, what do we have? We have the valid root locus branch. So minus 0.5 is your valid breakaway point. And then you come to minus 1.5. So minus 1.5 is getting traced somewhere here, and this is also NRL. So it becomes invalid. So out of 3 breakaway points, by applying rule number 3, we found only 1 point is valid. Okay, only 1 point is valid. So this rule helps in validating the breakaway points. All right, fine. So that's about rule number 6 and connection of rule number 6 with rule number 3. Then we have rule number 7. So rule number 7 is something like intersection with j omega axis. Now intersection with j omega axis, somewhere we have heard. Okay, any guesses? RH criteria. In RH criteria, we have heard about the intersection with j omega axis, and this intersection with j omega axis is something to do with marginal stability. Because only at marginal stability, the system tends to be neither stable nor unstable. Alright, so how will you find the intersection point with j omega axis? By RH criteria. So first of all, you have to find f of s, which is 1 plus g of s into s. Once you have the characteristic equation, you need to construct RH take. RH take. And from the RH table, determine K margin or K mar. Right? What is K mar? K mar is the value of k which makes a particular row in root array a row of zeros, except for s to the power 0. So that particular value is called as k marginal. Now, once you get the k marginal, and if your k marginal is positive, that means to say if you get k marginal as a positive real number, you can say that the root locus intersects with j omega axis. Root locus intersects with j omega axis, and the roots are typically plus or minus j omega. Right. And how do you find the roots? Auxiliary equation. Auxiliary equation is found. Okay. So how to find the auxiliary equation? Nothing new, right? So construct an equation from the coefficients of a row which is sitting above the row of zeros. So auxiliary equation is found, and roots of a of s gives intersection point with j omega. So if k marginal is positive, you can say that root locus intersects with j omega axis, and when you construct the auxiliary equation and when you solve that particular auxiliary equation, you will find the roots of this nature, plus or minus j omega. So plus or minus j omega is nothing but the intersection point with j omega axis. On the other hand, if let's say suppose you get k marginal is equal to some negative real number, okay, if you get imaginary number, then it is an invalid case. You should get real number, either positive or negative. If you get k marginal as negative, then you can say that root locus doesn't intersect with j omega axis. Root locus doesn't intersect with j omega axis. What do you mean by that? It doesn't intersect. If it doesn't intersect, then where are you going to find the root locus? Whenever k marginal is negative, the root locus is not going to touch your j omega axis. So due to which entire root locus lie on LHS of plane. Very, very important. If k marginal is positive, it intersects with j omega axis. Find the roots of the auxiliary equation, that will give the intersection points. On the other hand, if k marginal is negative, then it doesn't intersect with j omega axis. So if it doesn't intersect with j omega axis, what's the point in finding out the roots? Even if you find out the roots, you will not get of the form plus or minus j omega. You will get a pair of real roots. So you can say that the root locus doesn't intersect at j omega axis. This is your rule number 7. Actually, for most of the problems, you can apply to rule number 7. Now, there are special problems in which you will have complex conjugate poles and zeros. If at all your transfer function is consisting of complex conjugate poles and zeros, then only you are supposed to apply the next rule, which is rule number 8. Alright. So there are totally 8 rules in rule. So let us discuss the final rule, which is rule number 8. So rule number 8 is called as angle of arrival and departure. Okay. Angle of arrival and departure. Okay. Arrival and departure. Similar to your flight, arrival flight and departure flight. Okay. So angle of departure. Okay. First, okay, fine. Let us consider angle of arrival. Angle of arrival is denoted by phi a, and phi a is written as (180 plus phi). Okay. So arrival is taken in positive sense, and leaving, that is nothing but departure, is taken in negative sense. So that way, you can remember this particular form. Now, why this 180 degree? See, this 180 degree is due to the presence of, due to the impact of angle condition, right? You remember the angle condition. Angle of g of s into h of s is plus or minus 180 degree, etc. Right. Where phi is equal to summation phi p minus summation phi z. I'll come to it. What is phi p and phi z? Similarly, angle of departure is denoted by phi d, d for departure, and it is given as 180 minus phi. 180 minus phi. Where phi is equal to, once again, phi p minus phi z. Summation phi p minus summation phi z. Now, when to apply phi a equation and when to apply phi d equation. So, equation phi a is applicable for complex zero, a complex conjugate. So, angle of arrival is applicable to only if you have complex zero in your transfer function. On the other hand, angle of departure is applicable if your transfer function is consisting of complex conjugate pole. One is applicable for 0 and one is applicable for complex conjugate 0 and complex conjugate 4. So, how to find phi p and phi z, phi p and phi z? I will discuss when I handle such problems. Alright. So that completes the construction of root locus. So far what we have done is we have just discussed the various steps involved in the construction of root locus, but we haven't constructed a root locus plot. Okay. So in the tomorrow let's take a few examples. Okay, wherein let us take up some physical transfer function and let us try to construct the root locus plot. So that's it for the day. Thank you so much.